Okay, welcome back. Here we go for part 2 of section 7.1. We're working on sets. We're working on operations on set. And we'll take a look at some more set operations. So we've got element and subset. And now we're going to take a look at the intersection, the union, and the complement. Now, the mathematical definition of the the intersection of two sets says that the intersection of two sets is a set containing all elements that are common to both sets. Right? This would be the set builder notation of that. Right? And so we've got our symbol on the left-hand side. This is going to be our symbol for the intersection. It kind of looks like an upside down, it's not really a U, but kind of like an upside down U. And it reads the set of all x's such that x is an element of A and also an element of B. So it is all the elements that they have in common. Right? If it so happens that you have two sets that have no elements in common, we say those two sets are disjoint. We say two sets are disjoint if their intersection is the empty set. So what I mean by that is if I told you that A was 2, 4, 6 and B was 3, 5, 7, then A intersection B would be the empty set because they have nothing in common, right? But if I change that a little bit, if I change this problem and I say that B is the set 2, 5, then the intersection is just the element 2 because it's the only element that they share. Right? The union of two sets is the set that contains all of the elements that are in either of the two sets. Right? And so it's set builder notation right here. We got to focus on that word or. A union B is a set of all x's where x is an element of A or x is an element of B. Now that word or is a tricky word because the mathematical definition of the word or is different from the common definition. The common definition is the exclusive or. It means you could have A, you could have B, but you cannot have both. That is not the definition that we use. We use the math definition. The math definition of or means you are in A or you are in B or you are in both, that you have both of those, right? And so if I said, what is A union B? Well, you would take all of the elements from set A, all of the elements from set B, you'd lump them together and make one big set out of it. So it'll be 2, 4, 5, 6. Well, but wait, someone sure is asking, if the 2's here and the 2's there, shouldn't the 2 show up twice over here? No, we only put it in there once. So if there are elements in the intersection in the union, we don't repeat them. We just represent that element once. Okay? And then the complement of the set. And this is the tricky one down here. The complement's a little bit tricky. The definition says that the complement of a set is the set containing all the elements from the universal set that are not elements of the given set. Well, the definition puts it puts a new phrase, a new term in there that I don't know, universal set, right? So basically it looks like this. The universal set, it's the biggest set that you care about. Like if I were to say that the universe, U, is and I'm going to use words, the set of all good, well, let me get rid of the word good, all Ryan Reynolds movies. then that set would contain every movie that he's ever made. And then if I said set A was the set of good RR movies, what would the complement be? Well, then a complement is going to be everything that is in the universe, but not a good one. So it will be all the bad RR movies. Okay. So the universe tells you the set that you're working with. Okay. Everything that exists in my world is a Ryan Reynolds movie from now on. A is all of the good ones. B is the complement. So B is all the bad ones. Okay. Small set, big set. All right, let's take a look at some examples, some numbers. So here are some examples. Right? I've got a universe defined over here. My universe is the set 1, 2, 3, 4, 5, 6, 7, 8, 9. So it is the first 9 counting numbers, or however you want to word that. Right? A is the set 2, 4, 6, 8. That's my evens. From my universe, B is my set 1, 5, 3, 7. That's my odds from my universe, but not 9. So it's missing 9. And C is 1, 2, 3, 4. The first 4 elements of my universe. We're supposed to find all of the following. So what would A intersection C look like? Well, A intersection C says take all of the elements of set A, 2, 4, 6, 8, intersect that with set C, which was 1, 2, 3, 4. And so what does intersect mean to do? It means to look at those two sets and see what they share. See what elements are in common. There's a 2 in both of them. There's a 4 in both of them. I've got a 6 and an 8 over here, but I don't have a 6 and an 8 on the right in set C. I got a 1 and a 3 in set C, but I don't have those in set A. So then I would say that the intersection of A and C would be the set 2, 4. So there's my intersection. All right, so let's take a look at A union B. Let's see, A union B means take all the things that are in A. That's the 2, the 4, the 6, and the 8. Union that with B, which is the set 1, 3, 5, 7. So union says take all of these and all of those and put them together in one big set, but don't rewrite any duplicates. So it will be 1, 2, 3, 4, 5, 6, 7, 8. Now, earlier when we were talking about the definition of a set, we said that the order is unimportant. So the fact that I'm putting these in numerical order is not relevant or important or required. That's just my brain says these need to be in order. I can't have them out of order. That's crazy talk. Okay. All right, moving right along. What's being asked here in this one? Let's see. My job is to find the complement of A. So just a note about complement. This textbook uses the apostrophe, but you will sometimes see this with a little c. You will also sometimes see this with a bar over it. All of those mean the same thing. They mean the complement of A. My personal favorite is the little c up there, this second one here, but this textbook doesn't use that. The reason I like that is it's very hard to confuse that with something else. I don't like A complements because of this. Sometimes when I'm drawing these things, I do that. And is that the complement or is that something else? Is that just a stray mark on the paper? So I don't care for the apostrophe personally, but I understand that it's the one we're going to use. And the reason that we're going to use it is because it is the one the book's using. Okay. All right, so here we go. A complement, A complement. A complement is all of the elements that are in the universe but not in A. And since A was, I don't want that arrow thingy anymore. Since A was 2, 4, 6, 8, the evens from our set, then a complement would just be the odds. 1, 3, 5, 7, and 9. It's everything in the universe, take away 2, 4, 6, 8. Right? All right, more, because I know you want to do more. A intersection B complement. So A, 2, 4, 6, 8, intersection B complement. B was 1, 3, 5, 7, so B complement would be 2, 4, 6, 8, 9. Intersection, what do they share? What do they have in common? 2, 2, 4, 4, 6, 6, 8, 8, not the 9. So then A intersection B complement would be 2, 4, 6, 8. Now technically you would not be wrong if you wrote this. A intersection B complement is just A, because for this example, the intersection is A. All right, moving right along. A complement union C. Well, A complement, we already said, was 1, 3, 5, 7, 9. And we're going to union that with C. C is 1, 2, 3, 4. And when we union them, we take all of these guys, all of those guys, put them together and make one big set out of it. So then A complement union C is 1, 2, 3, 4, 5, 7, 9. The last one we have to take a look at here is C intersection B. All right, C is the set. 1, 2, 3, 4. We're taking the intersection of that with B. B is the set 1, 3, 5, 7. We're looking for the intersection. Intersection means the elements they have in common. There's a 1 here, a 1 there, a 3 here, a 3 there. That's it. So the intersection, C intersection B, is equal to the set 1, 3. And there's my intersection. Okay. Last thing we have to take a look at in this section, and then we'll move on to Venn diagrams, is the idea of subsets. Okay. A subset. Now we already took a look at the definition of a subset, but this question asks, how many subsets are there? So if I have a set that has k distinct elements, where k is just the number of elements in the set, so k will be something like 3 elements or 4 elements or 6 elements, whatever it is, how many subsets would that set have? And the formula says that there are 2 to the k subsets. So let's take a look at what we're talking about here. Suppose we have a nice, small, super easy set, the set containing the element 1. How many subsets would that set have? Well, it would have the empty set, and it would have the set containing 1, and those are the only 2 subsets that it would have. If I had a set B that had 2 elements in it, it would have the empty set as a subset. It would have the set containing the element 1 as a subset, the set containing the element 2 as a subset, and the set containing the elements 1 and 2 as a subset. So it would have 4 of them. So 2 of them, 4 of them. If I had a 3-element subset, 1, 2, 3, it's going to have the empty set. It's going to have 1, the element 1. It's going to have the element 2. It's going to have the element 3. It's going to have the element 1, 2. It's going to have 2, 3. It's going to have 1, 3. And it's going to have 1, 2, 3. So how many is that? That's 1, 2, 3, 4, 5, 6, 7, 8. That's 8 subsets. Well, if we use the formula up here, There's one element in this set, so 2 to the first is 2, so there's 2 subsets. There's 2 elements in the set, so 2 to the second is 4. There's 3 elements in the set, so 2 to the third is 8. So a set has a bunch of subsets. How many is a bunch? It's 2 raised to the number of elements, 2 to the k, where k is the number of distinct elements. Let's take a look at our example here. A make-your-own pizza restaurant has the following toppings for pizza. You can say the set T contains pepperoni, sausage, red bell peppers, banana peppers, Roma tomato slices, red onions, and roasted garlic. And those are the toppings that you can choose from. How many possible pizzas could be made using these toppings? So what I want to do is I want to make a pizza. Well, I could have a pizza with just pepperoni, with just sausage, with just peppers, with just peppers, with just. So I can have a whole bunch of one element pizzas, or I could do pepperoni and sausage, or pepperoni and red peppers, or pepperoni and banana peppers, or. There's a lot of different ors here. But essentially what I'm doing is I'm saying, how many subsets exist? Because every subset of set T is going to be a pizza. And so the formula says find k, and then there will be 2 to the k subsets. Well, when I take a look at this set, 1, 2, 3, 4, 5, 6, 7. It appears that there are 7 possible toppings. So then we will have 2 to the 7th different pizzas, and 2 to the 7th is what? I'm going to grab a calculator. 2 raised to the 7th. There are 128 different pizzas. Now, a question that is sometimes asked at this point about this number 128. I know that one of the subsets is this guy. Is that a valid answer to this question? Is the empty set a valid pizza? Okay. Well, the empty set would be the pizza where you just didn't make any topping choices. Nothing, none of those. And so if I just had a plain cheese pizza, would that still be a pizza? And if you think the answer to that question is yes, then you would say that there are 128 pizzas. If you think the answer to that question is no, then you would just subtract out that empty set and say that there are 127 pizzas. And it's all going to be how you determine what's being asked here. Does this question imply that I have to use a topping? Or can I just simply say I want a cheese pizza and then I wouldn't have any of those toppings? Now, me personally, I think that it's okay to have a cheese pizza, a plain cheese pizza. And so I would say that there are 128 of these. Okay? All right, I'm going to end this video here. We're at 18 minutes. And then we'll come back and we'll start the next video down here with Venn diagrams and talk about Venn diagrams and set operations.